Formula of friction. Number 1, a body is placed on a rough surface. mg is the weight which is acting downwards, and R is the normal reaction force acting on the body. Fex is the external force which is applied on the body, which acts from its center of gravity, and limiting friction Fl acts in the opposite direction of Fex. Here limiting friction Fl proportional R, where R is the normal reaction, and finally we get Fl as equal μs dot R, which is the limiting friction or the force of limiting friction, at which if a body is at the verge of moving over the surface of another body, then limiting friction comes into play, where μs equal coefficient of friction, μs equal coefficient of friction, R equal normal reaction on the body applied by the rough surface of the other body, and here Fl equal μs dot R. Body was at rest, that means initial velocity u was 0, acceleration a was 0, and the body is at the verge of moving over the surface of the other. When limiting friction Fl acts, in that case the body should be at the verge of moving, and at equilibrium R equal mg. At equilibrium, normal reaction R equal mg in this case. R equal mg, normal reaction. Number 2 formula. Number 2 formula, bodies placed on a rough surface, and mg is the weight of the body which acts downwards, R is the normal reaction which acts upwards, Fex is the external force which is acted on the body, and here kinetic friction Fk acts in the opposite direction, and the body will be moving with an acceleration a in the direction of applied force Fex. In this case, kinetic friction Fk is proportional to normal reaction R, therefore Fk equal μk dot R, that is the expression of kinetic friction. Fk equal μk dot R, which is the expression of force of kinetic friction, or only kinetic friction. Force of kinetic friction. Where μk is the coefficient of kinetic friction. μk is the coefficient of kinetic friction. R equal normal reaction. R equal normal reaction acted on the body applied by the rough surface of the other body. In this case, R equal mg at equilibrium. Normal reaction R equal mg means weight of the body. Normal reaction is equal mg. Here the body moves with an acceleration a. In the direction of the applied external force Fex. Hence, ma equal mass into acceleration equal Fex minus Fk. External force Fex minus kinetic friction Fk. So this is the equation of motion of a body. And number 3 formula. If we plot frictional force versus applied force, this graph, applied external force is plotted along x-axis, and the force of friction is plotted along y-axis. Fex is the applied external force. And if we increase applied external force Fex, then force of friction will change in this way as shown in the graph, and we can draw a perpendicular from the maximum, from the highest point, and this imaginary line is the maximum value of static friction which is called limiting friction FL. And we can also draw a perpendicular from the highest point on the vertical axis or on the force of friction axis. This point is A, and then B and C. From A to B, force of friction decreases, and at A, applied external force Fx will be equal to Fl, and at A, force of friction F equal to Fl. So here this length, this perpendicular in the portion BC, if we draw a perpendicular from the portion BC on the horizontal axis, we get kinetic friction Fk, and that kinetic friction is constant. From O to A, static friction F is directly proportional to applied force Fex, and from B to C, kinetic friction or force of friction remains constant. That means force of friction is independent of external force. F is not function of Fex. Limiting friction is the maximum. Limiting friction FL is the maximum value of static friction. Is maximum value of static friction. From O to A, force of friction is static friction, and maximum value of static friction is limiting friction. Kinetic friction Fk remains constant in the portion B to C. In the portion BC, in the graph, kinetic friction is independent of applied external force Fex. If we increase Fex, kinetic friction remains constant. Limiting friction FL is greater than kinetic friction Fk. In the graph, FL is greater than Fk. Number 4, μs equal FL by R, which is coefficient of static friction or coefficient of limiting friction. Coefficient of static friction. Static friction means the force of friction which comes into play when the body is at rest over the surface of another body. Mu k equal Fk by R. Mu k equal Fk by R, where Fk is kinetic friction. So mu k equal Fk by R, which is coefficient of kinetic friction. When a body moves with certain acceleration, in that case we should consider coefficient of kinetic friction mu k. And if we divide mu k by mu s, we get Fk by Fl. As Fk less than Fl, so we can say that mu k less than mu s. Coefficient of kinetic friction is less than the coefficient of static friction. Mu k less than mu s or mu k less than mu l. Mu s can be denoted by mu l also. Mu s equals 0.7. Mu s equal 0.7 for a wooden block on a wooden surface. Mu s, the value of coefficient of static friction mu s is equal 0.7. Also mu k equals 0.4 for a wooden block on a wooden surface. Mu k is equal to 0.4 means coefficient of kinetic friction mu k is equal 0.4, and mu s equals 0.7 and mu k equals 0.4. Hence we can say that mu k less than. Number 5 formula, body is placed on a rough surface. This is the normal reaction R. mg is the weight which is acting vertically downwards, and here we can assume that mg and R acts from the lowest point of the body. An external force Fex is applied on the body and it will appear to act from its center of gravity, but limiting friction Fl acts from the lowest point of the body on the surface in contact. Fl is the limiting friction. Taking Fl and R as two adjacent sides of a rectangle or parallelogram, the diagonal of this rectangle is n. N is the resultant of limiting friction Fl and normal reaction R. N makes an angle theta L with the direction of normal reaction R. And this angle theta L is the angle of friction. O is the lowest point of the body. Along OY, normal reaction R acts. Along OX, limiting friction Fl acts. Towards right, the body is at the verge of moving. towards right, the body is at the verge of moving over the rough surface of the other body due to application of external force Fex, but the body does not move. In this case, theta L is the angle, theta L is angle ZOY, that is angle subtended by the resultant N with the direction of normal reaction R. This is angle of friction, angle subtended by angle which the resultant N of FL and R makes with the direction of R. Angle of friction which the resultant N of FL and R makes with the direction of R. With the direction of R, where FL is the limiting friction and R is the normal reaction. Also, μs equal tan theta L, that is coefficient of static friction or coefficient of limiting friction, is equal to tangent of angle of friction. Therefore, theta L equal tan inverse theta L. Theta L equal tan in. Number 6 formula. We can draw two slants of a cone or of friction cone. This is another slant of friction cone, and friction cone is an inverted right circular cone. Here we can draw the friction cone in this way. This is the normal reaction R, which will be assumed as the height of friction cone, and this will be the circular base, circular cross section of friction cone. We get friction cone, which is an inverted right circular cone having limiting friction FL as radius, normal reaction R as height, and resultant N as one of its slant. N is the slant of the cone. N is the resultant of FL and R. Here FL is the radius of the circular cross section of the friction cone. This is friction cone. Friction cone. For friction cone, which is an inverted right circular cone, inverted right circular cone, which is assumed when a body is at the verge of moving. In this case, for friction cone, radius is FL or limiting friction, height equal R means normal reaction, slant is what the resultant N, aperture is equal twice of theta L. 2 theta L means twice of angle of friction. So theta L is the angle of friction. Number 7 formula. We can draw an inclined plane, horizontal plane and the vertical plane. AB is the inclined plane, AC is the vertical plane. Theta R is the angle of repose, which is the angle at which a body is at the verge of moving down the inclined plane AB. This is a body whose weight mg acts vertically downwards. The weight mg is resolved into two rectangular components. This component is mg cos theta, which is perpendicular to the inclined plane AB. Other component is mg sin theta. This component is mg sin theta. Mg sin theta rectangular component acts parallel to the inclined plane AB. We can draw the imaginary rectangle assuming weight mg as its diagonal, and two rectangular components are mg cos theta and mg sin theta. Mg cos theta rectangular component is perpendicular to the inclined plane AB, and limiting friction FL acts up the inclined plane. Limiting friction FL acts up the inclined plane so that the body is at the verge of moving down the inclined plane, and this is what normal reaction R, which acts perpendicular to the inclined plane AB and upwards. The body has a tendency to move down the inclined plane. The body is at the verge of moving down the inclined plane under the action of the rectangular component mg sin theta. As mg sin theta acts down the inclined plane, normal reaction FL acts up the inclined plane to oppose the motion of the body. In this case, theta R is angle ABC, angle of inclination, which is the angle of repose. which is the angle of repose or angle subtended by the inclined plane with the horizontal plane BC, at which a body is at the verge of sliding down the inclined plane or is at the verge of moving down the inclined plane AB. That is called angle of repose. Moving down the rough inclined plane AB. Theta R is angle of repose. At this equilibrium condition, at equilibrium, limiting friction Fl equal to mg sin theta, normal reaction R equal mg cos theta. Also, μs, coefficient of static friction, is equal to tan theta R. Coefficient of static friction or coefficient of limiting friction μs is equal to tangent of angle of repose theta R. And we know that μs is equal to tan theta L, where theta L is the angle of friction. μs equal tan theta R and μs equal tan theta L. Therefore, we can say that theta R is equal to theta L, angle of repose for a body on an inclined plane. Theta R will be equal to angle of friction theta L. Number 8. Again, we can draw an inclined plane AB. Angle of inclination is theta. A body is placed on the inclined plane. Its weight mg acts vertically downwards as shown in the figure. Mg is the weight of the body which acts vertically downwards. This is the rectangular component of mg. This angle will be again theta. So here we can make a correction. Theta, angle of inclination will be theta, and theta is greater than theta, means angle of inclination is greater than angle of repose. We can draw another rectangular component of the weight mg. Another rectangular component of the weight mg. We can draw the imaginary rectangle, assuming mg as diagonal. Mg cos theta and mg sin theta are the rectangular components, such that mg cos theta rectangular component is perpendicular to the inclined plane AB. Mg sin theta component will be parallel to the inclined plane AB. And this is normal reaction R, which acts perpendicular to the inclined plane and upwards. R is the normal reaction, and limiting friction Fl acts. Not limiting friction here, the body will be in motion. That's why kinetic friction having smaller magnitude. Kinetic friction Fl having smaller magnitude Fk. Kinetic friction Fk will be acting up the inclined plane. Fk is the kinetic friction because the body will be moving with an acceleration A. A is the acceleration, and this is the direction of motion of the body down the inclined plane. The body will be moving with an acceleration A under the action of the rectangular component mg sin theta and Fk. Direction of motion of the body, and the body will be moving down the inclined plane with an acceleration A, as shown in the figure. In this case, the formula of the as theta greater than theta R, hence the body will be moving. The body will be moving or sliding down the inclined plane AB, down the inclined plane AB, down the inclined plane AB with an acceleration A. With an acceleration A. Therefore, the formula of acceleration A is equal to g bracket open sin theta minus mu k cos theta. Here mu is the coefficient of kinetic friction. A equal g sin theta minus mu cos theta, where mu is actually mu k or coefficient of kinetic friction. This is acceleration due to acceleration of a body moving down a rough inclined plane. Moving down a rough inclined plane such that angle of inclination theta is greater than the angle of repose theta R, and the body moves down the inclined plane under the action of its rectangular component mg sin theta. Number 9 formula. In this case, we have to find the expression of minimum force required to move a body up the inclined plane, provided angle of inclination theta is less than theta R. In this case, the formula of minimum force required to move the body. So, Fx equal mg bracket open sin theta plus mu cos theta. So Fex equal mg sin theta plus mu cos theta. This is the minimum force required to move a body up the inclined plane provided theta less than theta r. The body will not be moving down the inclined plane under the action of the rectangular component of its weight. The body will be at rest on the inclined plane, and we have to move the body up the inclined plane, and we get the expression of minimum force required to move a body up a rough inclined plane. In this case, theta less than theta r. That's why theta r is the angle of, and where theta r is the angle of repose, theta less than theta r, and theta is the angle of inclination. Theta is the angle of inclination. As theta less than theta r, the body will be at rest, and an external force Fex should be acted on the body to move the body up the inclined plane. At equilibrium, external force Fex will be equal to net internal force acting in the opposite direction. Fex is equal to mg sin theta plus Fl. So in the diagram, Fex acts up the inclined plane, which is external force, and in the opposite direction, mg sin theta and Fl are acting down the inclined plane. That's why Fex is equal mg sin theta plus Fl. Number 10 formula. We have to find the expression of force required to move a body down an inclined plane. Fex is equal mg bracket open mu cos theta minus sin theta. Fex is the minimum force, required to move a body down an inclined plane. Minimum force required to move a body down a rough inclined plane. Fex equal mg bracket open mu cos theta minus sin theta, where mu is the coefficient of static friction. In this case, theta less than theta means angle of inclination ABC is less than the angle of repose. That's why the body will be at rest, and we have to apply a force Fex down the inclined plane. At equilibrium, external force Fex will be equal to net internal force acting in the opposite direction. Fex is equal to limiting friction Fl minus mg sin theta. And that's why we get Fex as equal mg bracket open mu cos theta minus sin theta. In diagram, Fex is the external force which is acted down the inclined plane, and limiting friction Fl acts up the inclined plane, and Fex will be equal to Fl minus mg sin theta. Number 11 formula. Work done to move a body from the point P to Q up the inclined plane is W equal mg sin theta plus mu cos theta into S, where S is the displacement. So W is the work done in moving a body, work done in moving a body up a rough inclined plane for a displacement S. Up a rough inclined plane for a displacement S. W equal mg bracket open sin theta plus mu cos theta into S. Fex is the external force which is acted on a body at the point P, and the body will travel from the point P to Q for a displacement S. From P to Q for a displacement S. S is the displacement up the inclined plane from the point P to Q.